Bismillahirrahmanirrahim. I welcome you to the 12th lecture of the series of lectures on advanced computer architecture. Today, the focus of our discussion will be multiple cycle pipeline data paths for floating point instructions. Last time, we discussed the design of pipeline data path, which is used for instruction level parallelism. Instruction level parallelism means that multiple instructions are to be executed in parallel using a single pipelined data path. Then we discussed the problems which may occur while using the pipeline data path. Here we found that there are three types of problems which can occur, known as the three types of hazards: the structural hazard, the data hazard, and the control hazards. The structural hazard is one which occurs when multiple instructions try to access a single resource. For example, when a single memory unit is needed for instruction fetch as well as data read or write for load or store instruction. Similarly, if more than one instructions try to write to a register file which has got only one write port, so these situations are known as the structural hazard situations. The data hazard occurs when an attempt is made to access data which is invalid. This situation may occur in different scenarios, and these scenarios can be explained by assuming that an instruction J follows an instruction I. Then what are the possible scenarios? The first scenario is known as read after write. The read after write hazard is one when instruction J tries to read an operand before instruction I writes it to the register or to the memory. This you can see from this slide with the help of these two expressions, where the instruction I is add to register R2 the value from register R3 and place the result in register R1. Whereas the instruction J is subtract R3 from R1 and place the value in R4. Here, when the jth instruction tries to read the operand from R1, the correct value of the operand is not available in R1 because the ith instruction writes the value into register R1 during the fifth stage. This situation is known as the data dependent situation. The second type of hazard is known as the write after read, that is WAR. This is the situation which is known as anti-dependence situation. Here, the instruction J tries to write an operand before instruction I reads it. So the wrong operand is basically obtained. However, in this particular situation, no value is transmitted. You can see this from this example over here, where instruction I, which is subtract R4, R1, R3, means that the R3 is to be subtracted from R1 and the value is to be placed in R4. Whereas the jth instruction is one where the sum of R2 and R3 is to be written into R1. So in this particular case, R1 is read before R1 is written. But this is not transmitting any wrong result. However, this type of dependence is also known as the name dependence, and it can be overcome by renaming the registers. For example, if instead of register R1, we use a temporary register or rename it by some other register, then this type of hazard can be removed. The third situation exists when instruction J tries to write an operand before instruction I writes it. This type of hazard is known as write after write hazard, and it is also known as the output dependence. Here you can see it from this example, where the ith instruction is to subtract R3 from R4 and write the result in R1. Whereas the second instruction also adds R2 to R3 and places the result in R1. Here, the jth instruction writes the operand before the ith instruction. So it is leaving the wrong result over here. The third type of hazard, which we talked about last time, is known as the control hazard. The control hazard is one which occurs when an attempt is made to branch before evaluating the condition. This, in fact, results in fetching a wrong instruction and placing it in the pipeline. Here, in all these three types of hazards, that is, structural hazards, the data hazard, or the control hazard, one thing is common, that we cannot proceed further until and unless this problem situation is over. And this suggests that we have to stall before proceeding to the next stage operation of the pipeline. However, we also noticed that the stall operation degrades the performance of the pipeline. The other techniques which we discussed last time to overcome these problems of the pipeline are, in case of structural hazard, we can use multiple functional units so that there are two memory units. One is, say, for the instruction operation, and the second is for the data, known as the instruction memory and the data memory. Similarly, in order to avoid the write-back structural hazard, we can avoid it by providing more than one write ports. Then we also talked about the data hazards, which can be avoided by using forwarding technique, where the data which has been evaluated or determined and is available in a pipeline register can be read instead of reading it from the destination register after the write back operation. For the control hazard, we discussed number of methods such as the predict technique, where we discussed predict if the branch is always taken, or predict if the branch is never taken. Similarly, the other technique which we talked about was known as the delayed branching. So with these much discussions about the pipeline data path design and the problems which can exist in a simple pipeline structure, today we will continue our discussion onto the pipeline design from the point of view of the instruction level parallelism for the long data. For example, for the double word data or the floating point data. So for this purpose, first of all, let us see what is a floating point data and how we can perform different operations onto a floating point data. I hope that you basically know the difference between the integer numbers and the real numbers and how these numbers are represented. The integer numbers are represented by a single word, whereas the floating point numbers or the real numbers are represented as floating point numbers, which has got two parts, that is the exponent and the significand. And in order to perform arithmetic operations onto the floating point number, we have to deal with the exponent and the significand separately. Therefore, this means that an algorithm is to be implemented in order to perform the arithmetic operations onto the floating point data. For this purpose, let us consider a simple example of adding two floating point numbers. What are different steps which one has to take? For this purpose, let us have a look onto this flow chart. Here you can see that the add operation can be performed by using the following steps. In step 1, the exponents of two numbers are compared. The smaller number is shifted to the right till its exponent matches to the larger exponent. Then in the second step, we add the two significants. Then we normalize the sum, and in order to normalize the sum is shifted right and incremented, or shifted left and decremented. In the step 4, if no overflow or underflow occurs, then we round the significand to the number of bits. And if further normalization is not required, we stop this process here. Otherwise, we can go back to the normalization step, that is the step number 3. So this way, you can see that the floating point functional unit must be redesigned to perform all these operations, and this type of functional unit will have longer latencies and initiations are repeat than the integer type ALU. Here, before proceeding further, let me define what do we mean by the latency of a functional unit. The latency of a functional unit is defined as the number of cycles between the instructions those produce a result and the one that uses the result of the operation. Whereas the initiation or repeat interval is defined as the number of cycles that must elapse between issuing of two operations of the same type. This means that if we have to issue one instruction repeatedly, what is the time in between the issuance of these two instructions? It is known as the repeat interval or the initiation interval. Now, with the help of this slide, you can see in general the latency and repeat intervals for different type of functional units which can be used to design a longer latency pipeline circuit. Here we are considering typical structures where for integer type ALU, it has got latency of 0 and repeat interval is 1 clock cycle. This is because of the fact that the result is used on the next clock cycle for an integer type instruction. Whereas for the load, it has got a latency of 1 because the result is used or loaded into registers after one intervening cycle. Whereas for the floating point add operations, as we discussed earlier, it has got longer latency, and in this typical example, the latency is equal to 3 and initiation is 1 cycle. Whereas for floating point or integer multiply, because it is, again, we have to run some algorithm for this purpose, and it requires more than 1 cycles. Here, the latency is equal to 6 and initiation interval is equal to 1. Whereas for the floating point or integer divide instruction, the latency is 24 and initiation is 25. Now, in order to see how we can design floating point pipeline structure, you can look into this diagram where you can see that the execution stage here is not pipelined. Therefore, no other instruction using a particular functional unit may issue unless previous instruction leaves. The floating point operations simply loop for number of stages equal to latency plus 1 when they reach execution stage. They proceed to memory and write back to complete the execution only when they have finished execute stage. Now, this example, which we have just discussed, is when the individual functional units are not pipelined. This means that in the add unit, we cannot provide the next instruction for the 4 clock cycles. For multiply, it requires 7 clock cycles to complete the operation. However, we can enhance the performance of floating point pipeline by using pipelined functional units. This you can see from this expanded diagram where each functional unit has been expanded. Here you can see that the adder and multiplier are fully pipelined and have depth of 7 stages and 4 stages respectively. Thus, the structure allows up to 7 outstanding multiply and 4 outstanding floating point adds to be pipelined. However, over here you can see that in this particular case, we have to add the pipeline registers in between the internal stages of the floating point functional unit. For example, in the floating point add unit, to convert it to a pipeline floating point add unit, a pipeline register is to be included in between A1 and A2, A2 and A3, A3 and A4. Similarly, for multiply operation, the functional unit can be pipelined if we add pipeline registers between M1, M2, M2, M3, M3, M4, M4, M5, and up to M6 and 7. In this particular example, we are not pipelining the divide functional unit because this divide functional unit will become very, very complicated and it will not be possible to convert it in a pipeline format simply by adding pipeline registers. A very complex hardware is to be added for this purpose. Therefore, usually the divide functional unit is not pipelined. Now let us consider a few typical examples with the help of which we can see the performance of pipelined floating point data path using pipeline functional units. So first of all, let us consider the unpipelined functional unit. Over here, with this timing diagram, we can very easily explain how a floating point pipeline data path works. You can see that in this example, we are considering sample program of 5 operations, where the first operation is multiply, second is add, the next is load, and the last is the store. Now, in these instructions, here the .d with all instructions shows that we are considering double precision floating point data. The floating point load store uses 64-bit data path to the memory, which means its internal bus is of 64 bits. Furthermore, over here you can see that the stages, they show where the data are needed, whereas some stages which show where the results are available. And you can very easily see that the multiply instruction requires 11 cycles to complete the operation, whereas the add instruction can complete the operation in 9 cycles, and the last store instruction can complete the operation in 8 cycles, whereas the load instruction takes minimum time and it is fetched in 3rd clock cycle and it is completed in the 7th clock cycle. So this shows that different instructions are taking different time. How it affects the overall performance, this we will discuss after a while. Whereas now I will talk about what type of problems can occur in this particular situation. Here, all the functional units are not fully pipelined. For example, in this case, the divide is not pipelined, therefore hazards may occur. The instructions are having different times to completely execute, and there are chances that more than one register writes may occur at the same time, which in fact leads to the structural hazard. Similarly, over here, the instructions are no longer reaching the write back stage in order. For example, as you have seen in this example, that the multiply instruction performs the write back operation in 11th clock cycle, and store instruction performs the write back operation in the 8th clock cycle. So this shows that there are situations which can exist leading to write after write hazard. However, the write after read hazards are not possible in pipelined functional units because the registers are read in the instruction decode stage. Whereas the stalls for read after write data hazards may be more frequent because the latency of the operation is longer and it may give rise to the read after write hazard. Now let us consider another example of floating point pipeline structural hazard which may exist. For this purpose, we can consider this example program which is shown over here. We are considering three situations. The first instruction is the multiply instruction, whereas the second instruction and third instruction may be any one, whereas the next floating point instruction is add, and the last one is the load instruction. Here you can see that the three write backs operations appear in the 11th clock cycle, which leads to the structural hazard. And this is due to the varying length or the varying latency of different types of instructions. However, as we have noticed that all instructions check hazards in instruction decode stage. Therefore, we can perform the following three types of checks. For structural hazard, we have to wait until the required functional unit is available. Once we know that the functional unit is available, then the instruction is issued for execution purposes. Similarly, the second check is for the read after write type data hazard. Here, we wait until the source registers are not listed as pending destination register that will not be available. And after making this check, the instruction is issued. Whereas the third check is for write after write hazard. This write after write hazard is determined in if any instruction in A1, A2, etc., or M1, M2, etc., has same destination as this instruction. So this means that we can have overcome the problem of hazards in case of pipeline functional units by performing these checks at the instruction decode stage before issuing the instruction for execution purposes. I will explain this thing further with the help of certain examples that how crucial these stages are and how different situations may occur when we consider some exceptional cases. As an exceptional case, let us consider this example, where in this example of classic pipeline, where both the data and structural hazards are checked during the instruction decode stage. In this program, which you can see over here, the code sequence does not depict any dependence problem. However, we can see that the problem may arise when instruction add.d or subtract.d provides its result before the divide instruction. So this is the situation which is known as the out of order completion. This out of order completion leads to number of other problems which we can look into details by using different techniques. We can overcome the problems of data hazard by using either the stall operations, or in case of functional point operations, we can do this by using a technique known as scheduling. Scheduling is a technique where the different stages of pipeline are organized to perform different operations onto the instructions, and also look if out of order execution is possible. For this purpose, usually two different approaches are used, known as the static scheduling and dynamic scheduling. The static scheduling is one where software methods are used to schedule the instructions which are to be executed in a particular sequence. Whereas the dynamic scheduling is one where some hardware techniques are used to schedule the operations which are to be performed by different pipeline functional units. However, for static scheduling, we will look into these techniques at some later stage, whereas today we will start our discussion onto the dynamic scheduling, which is the method used by hardware to schedule the instructions for out of order execution. For this purpose, let us have a look onto this problem. Here you can see that the first instruction is divide, second instruction is add, and the third instruction is subtract. The subtract instruction does not depend upon the first or second instruction. So this means that the first instruction can be executed in any order, whereas the second instruction, which is addition of the contents of register F8 and F0 and placing the result in F10, it involves the register F0, which is to keep the result of first instruction. So this means that this second instruction has got data dependency, whereas the third instruction does not have any data dependency. So now if this program is to be executed in a floating point pipeline structure, then the second instruction has to stall till the data has been written into the register F0 and it is to be used by the second instruction. But we know that the addition operation is performed in a separate functional unit and multiply operation is performed in another functional unit, and multiply operation has a latency of 24 in our previous example. Therefore, the add instruction cannot be executed till 24 clock cycles. So this means a very long stall operations are needed. Whereas we can enhance the performance of the pipeline structure by executing the third instruction before executing the second instruction. So this situation is known as the out of order execution. So this is one way to enhance the performance of pipeline structure and reducing the number of stall operations. And this can be done if we are ready to schedule the instructions which are to be executed in a different sequence. The hardware technique used to schedule the execution of instructions out of order is accomplished by using a simple technique known as the scoreboard technique. The scoreboard technique is one where we maintain different tables which contain the information regarding the status of different registers and different functional units which are used for different operations during the execution of some instruction. These registers are continuously monitored and they instruct which particular instruction is to be issued at what instant of time. Now, as I discussed earlier, that it is the instruction decode when we can find out whether some hazard may exist or not. Therefore, in order to implement the scoreboard technique, the instruction decode is separated into two parts known as the instruction decode and issue. In our simple pipeline structure, we know that instruction decode stage performs two operations. That is, first, the instruction is decoded, and secondly, the registers are read to provide the values of the operands to the execution unit. This process of providing operands to the execution units is known as the issue operation. However, in the case of scoreboard implementation, the instruction is decoded first, and then we check whether some hazard exists or not. If no hazard is existed, or if there is no data dependency of this instruction onto some previous instruction, then this instruction is issued for execution purposes to the execution unit. So this way, basically, we first check the hazards, and then if no hazard exists, then we issue the instruction for execution purposes. So this technique basically suggests that we can avoid stall operations and we can perform out of order execution if we know a particular instruction which may give rise to some data dependency or not. We can look into this example over here. In this case, the subtract instruction does not have any data dependency onto the divide and add instruction, whereas the add instruction has got the data dependency onto the first divide instruction. So this means that if we issue first the divide instruction is fetched, then it is decoded, and as it is the first instruction, therefore it is issued for execution purposes to the divide functional unit. Then the second instruction is fetched and it is decoded. Now, as the second instruction has got data dependency onto the previous instruction, therefore this instruction will not be issued. Rather, the third instruction is fetched and it is decoded. And as the third instruction does not have any data dependency onto the first and second instruction, therefore this can be issued to a respective functional unit for execution purposes. So, whereas this information is also made available in the tables which are maintaining the record of which instruction has been issued and what is the current status of this instruction at a particular instant of time. This technique is known as the scoreboard technique. We will discuss this scoreboard technique with the help of some examples next time. And we will show that how we can execute different instructions out of order and how we can minimize the number of stalls, hence enhance the performance of pipeline data path. With this today, I will end by summarizing what we have discussed so far. Today, we talked about the extension of pipeline data path by providing the pipelines with longer latencies. For example, such a pipeline structure will be using multiple functional units for different types of operations, and these operations require or offer different latency and different initiation intervals. Basically, this particular technique of enhancing the pipeline structure is quite useful to handle instructions of varying latencies. Moreover, today we discussed in details the different classes of data hazard and how we can overcome these hazards when we are using some floating point pipeline structures. This much discussion onto this, I will like to refer you to your textbook. You can go through the appendix given at the end of your book and solve some problems, particularly the problem given at the end of the appendix as the exercise A8 and exercise A9. This will give you better explanation and it will clear the concept of this pipeline structure in a much better manner. So at this stage, I will conclude by saying that the pipeline architecture can be expanded by using multiple stage functional units, and these multiple stages can be used to enhance the overall performance of the system. Next time, we will take up the dynamic scheduling by first of all discussing how a scoreboard technique can be used to schedule out of order execution of certain instructions which do not have data dependency onto the previous instructions. With this much discussion today, I conclude here and say you Allah Hafiz.